Morning, ladies and gentlemen, or good afternoon, whatever the case may be. Today we're going to talk about inverse functions, Unit 5, Lesson 2. In Unit 5, Lesson 1, we determined what a one-to-one function was. By definition, a one-to-one function, every element in the domain of f of x maps to one and only one member of the range of x. And if we remember, a one-to-one function is either always increasing or always decreasing. So always increasing or always increasing or decreasing. That's how we're going to determine graphically if a function is one-to-one. If the function is always increasing or always decreasing. And we remember that from Unit 5, Lesson 1. So that's what Unit 5, Lesson 1. Today we're going to talk about inverse functions, what the heck we're talking about. So here's a function, here's a mapping. This right here is a mapping. This is a graphical representation of a particular function. This is a discrete function because we're only talking about a countable number of domain and ranges. Here we have 2 that maps to 5. We have 3 maps to 8. And notice the arrow here starts at 3, ends at 8, starts at 5, ends at 11. 5 maps to 11, and I have 8 that maps to 15. This is called a mapping. And this is a one-to-one function, and this is the domain of that one-to-one function, and this is the range of that one-to-one function. And this is the rule. The rule simply, in this case, there is no analytical rule. It's a mapping rule where 2 maps to 5, and etc. So what do we know? We know that f of 2 is 5, f of 3 is 8, f of 5 is 11, and f of 8 is 15. And here are our points. 2, 5, 3, 8, 5, 11, 8, 15. These are the points on f of x. These are the points on that function. And it is a one-to-one function because every element in the domain only maps to one and only one member of the range. So we can tell that, and if we graph that, we could certainly see that it passes the horizontal line test. That's the other reason we know if a function is one-to-one, if it's always increasing, always decreasing, or passes the horizontal line test. Don't forget that either. That's the information that we covered in Unit 5, Lesson 1, 5.1. Okay, and this is because every element in the domain maps to one and only one range. So in this case, the domain, if a function is one-to-one, then that function has an inverse. And this is the key thing right here. If a function is one-to-one, then that function has an inverse function. And that's what we're talking about in this unit, inverse functions. So all one-to-one functions have inverses. This is key. Whoa, where'd you go? Right here. This is key. This is a big key right here. The domain of the inverse function is the range of the original. The range of the inverse is the domain of the original function. This is, I gotta tell you, this is like a 5-star information right here. This is the most important property of inverse functions, is that the domain becomes the range becomes the domain. The notation for the inverse function is kind of funky. If f of x is a one-to-one function, then the inverse function exists, and it is denoted by this f of -1. And we call this f of -1. This is red, the inverse of f of x. And what we need to realize is that f to the -1 does not equal 1 over f of x. And this is going to be a little bit confusing because we do know that x to the -1 is equal to 1 over x. That's true. That's a property of exponents. This f to the -1 of x does not equal 1 over f of x. This is just the notation for the inverse of f of x. So it's all about the notation of the inverse. Okay, so if I'm talking about that above function that is indeed one-to-one, because every element in the domain maps to only one member of the range, as it does, the inverse exists. And so if we can talk about this inverse fairly easy. And what we're going to do, we're going to use this stuff right here, the domain, becomes the range becomes the inverse. And if I look back up here, this is the range, this is going to be the domain of the inverse, and this is the domain of the function. This is going to become the range of the inverse. And so here we go, because I'm going to create a mapping for the inverse of that guy up there. Well, here is the range of the original function, and this is going to be the domain of the inverse. These numbers here were the domain of the original function. They become the range of the inverse. And we see the inverse mapping is 5 maps to 2, 8 maps to 3, 11 maps to 5, and 15 maps to 8. So this is the mapping of the inverse of f of x. And I could actually talk about the points on the inverse as well. What are the points on the inverse? Well, here you go. 5, 2, 8, 3, 11, 5, 15, 8. And if I look up here at the points of the original function, let me zoom out. So let me see if I can't get a better picture where I can look at. Yeah, I can. Well, I'm going to zoom out just a little bit more here. Thank you. Put about 200%. There we go. And I'm going to zoom down here a little bit. And look at these points here. 2, 5, 3, 8, 5, 11, 8, 5. These are the points on f of x. Well, here, these are the points on the inverse function. It's pretty easy to straighten. At the beginning of inverse, it's pretty daggone easy. And look at this. The 2, 5 becomes 5, 2. 3, 8 becomes 8, 3. 5, 11 becomes 11, 5. And 8, 15 becomes 15, 8. And I can only do that because f of x was a one-to-one function. And since f was a one-to-one function, I can talk about this inverse function. Okay. Let's go to page 2. Let's zoom out here and go to page 2 here. And let's go to page 2 here. And here we go. Here's the most important property of inverse functions. The domain of the original becomes the range of the inverse. The range of the original becomes the domain of the inverse. In other words, if this point AB is on the graph of f of x, then BA is on the graph of the inverse. That's very, very important. So let's do an example right here. Example number 1. Consider the function defined by the set of ordered pairs 3, 7, 5, 8, 7, 9, and 9, 10. F of x is a one-to-one function, and I'm going to create the mapping for f of x. Here's the domain, 3, 5, 7, 9. These are the x values, and we know the domain are the x values. I have a 3, 5, 7, 9. And what does 3 map to? 3 maps to 7. 5 maps to 8. 7 maps to 9. And my 9 maps to 10. And this is the domain that I have listed here. And 7, 8, 9, 10. This is the range that I have listed here. And I have the actual mapping drawn. 3 maps to 7. 5 maps to 8. 7 maps to 9. And 9 maps to 10. So you should realize where I'm going with this. Where I'm going with this is I want to sketch the mapping for the inverse function and then name the domain and range of the inverse. Well, I'm going to tell you right now, this is going to be the domain of the range, pardon me, the domain of the inverse, and this is going to become the range of the inverse. So this is, if you take a deep breath and make this simple, it will be easy to figure out. Okay, so let's sketch the mapping for the inverse. And we realize, just like I said, the domain is going to be 7, 8, 9, 10. The range is 3, 5, 7, 9. And what does 7 map to? Well, 7 is going to map to 3. Bam. 8 is going to map to 5. 9 is going to map to 7. And 10 is going to map to 9. And make sure that when you do these mappings, that you certainly use these arrows. You just can't have a straight line. You have to have arrows. And that determines 10 goes to 9. 9 goes to 7. And this is the domain, just whoopsie. This is the domain of the inverse, and this is the range of the inverse. And the domain was the range, and the range was the domain. Pretty easy stuff, really, at the beginning. And you know it's going to get a little bit more complicated. So let's do an analytical function here. Consider the continuous. Everything we've looked at so far have been discrete functions. This is a continuous function because this is a linear function. It's a linear function written in point slope form. And we know from 5.1, unit 5, lesson 1, that all linear functions are one-to-one. Therefore, the inverse exists because it is one-to-one. And what I want to do for this particular example is I want to find and name the points associated with each function value. So if I want to, let's do an eraser here. Let's erase these bad boys here. I did this on a previous example. Okay, let's go f of negative 4. Well, f of negative 4, what's f of negative 4 going to be? I'm going to put negative 4 in here. This is going to be 3 plus 1/5 times negative 5, negative 4 minus 1. 1/5 times negative 5 is negative 1. 3 plus a negative 1 is going to be 2. So that's going to tell me that negative 4, 2 is going to be on, that's a point on F, putting negative 4 in. And if I put 1 in, 1 minus 1 is 0, F1 is going to be 3. So the point 1, 3, these are the points on F, and I want to find the name, the points associated with each function value for this particular function. And f of 6, what's f of 6? 6 minus 1 is going to be 5. 1/5 times, well, I'll just write it down. This is going to be 3 plus 1/5 times 5. 1/5 times 5 is 1. 3 plus 1 is 4. So this 0.64 is on that linear function. So I have 3 arbitrary, well, not arbitrary, 3 points on that linear function. And I know this is a continuous linear function. It's continuous and increasing. It's always increasing. It's always increasing because the slope is 1/5. That goes back to our discussion about linear functions, putting a lot of things together. What I want to talk about, since the inverse does exist, and the inverse does exist because the function is always increasing, is I want to find some points on the inverse of f, i.e., I want to find 3 points on f inverse. Well, I did it. Look at this. A, B, BA, AB, BA, AB, BA. So here's 3 points, negative 4, 2, 3, 1, and 4, 6. Those are 3 points on the inverse function. One of the things that we're going to learn how to do is actually find the rule for the inverse function if I do have a one-to-one function. And that's what we're going to do on the next page. So let's go to the next page. And here is the formal analytical definition of the inverse function. Consider f of x a one-to-one function and its inverse, f inverse. If f of x is a one-to-one function, its inverse does exist. It's called f of negative 1. And we noticed from last week, we did review some stuff about composite functions. Here's the analytical definition. If f of f inverse equals x, and f inverse of f of x equals x, that tells me that f and f inverse are one-to-one functions. And this is probably going to be the most difficult thing that we do about inverse functions. Is showing that when 2 functions are inverses, and what we're simply going to do is we're just going to do the composite f inverse of f of x. If they both equal x, they both have to equal x, then we know f and g of x are inverses of each other. So let's do an example of this. Okay, so I have two linear functions right here. I have f of x, 2 plus 1/3 x minus 5, and g of x, 5 plus 3 x minus 2. I want to determine whether these guys are inverse functions or not. Okay, so this is what I'm going to do. I'm going to go f of f inverse. This is the first thing I'm going to do right here. And then I'm going to do f inverse of f of x. So I'm going to go f of g. And f of g, what am I going to do? Wherever I see x, I'm going to put g. Well, this is g. And if I look at this guy right here, I'm going to circle that in yellow. I keep circling the wrong thing. This is g right here. So what does f tell me to do? It says 2 plus 1/3 times something minus 5. What's that something going to be is g. And this is g right here. And so now I'm going to do some basic arithmetic here. And if I look inside the parentheses, 5 minus 5 is 0. So I have 2 plus 1/3 times 3 times x minus 2. And this is 1/3 times this product. 1/3 times 3 is just 1. So what do I have? I have 2 plus x minus 2. 2 minus 2 is 0, and I have x. So now I have showed that f of g of x is equal to x. So I ask you to pause the video, and I mean, this is just a little bit of analytical work here that you had to do. Just pause the video and think about what I did. Verify that it does equal x. And you're going to have some exercises to do on your own. And what I want to do now is I want to find f inverse. I want to find g of f. Because I think that g is the inverse. I think that g of x is equal to f inverse. And that's what I want to happen. So I'm going to go g of f and see if it equals x. So here's g of f. This guy right here, same thing I did before. This is my f. And g says to take 5 plus 3 times something minus 2. Hopefully that's equal to x. I'm going to put f in there. And again, I have 2 minus 2 is 0. And I have 3 times 1/3, which is 1. What do I have? Looks like I have 5 plus x minus 5, which is x. And that's very nice. So now I have f of g is equal to x. And I have g of f is equal to x. So bam! These two functions are indeed inverses of each other. They are inverses. So therefore I know that g of x is the inverse of f of x. Why? Because of the analytical definition of the inverse. So make sure you get that copied down very carefully. Okay. The last thing we're going to do in this video is we're going to find the inverse of a linear function. And we have to be very careful. We're going to do a lot of this. And I'm going to give you the nice steps to find the inverse. So here we go. I want to find the inverse of this guy right here. I know the inverse exists because this is an increasing one-to-one function. It's increasing because the slope is 1/3. And you might have to go back and review some stuff about linear functions. So it's always increasing because of the slope is 1/3. So therefore the inverse exists. So I want to find, my objective here is to find this guy right here. Step number 1, I'm going to put y in for f of x. So I'm going to put y in for f of x. Here's my function. I'm going to put y in for f. So I have y is equal to 2 plus 1/3 x plus 5. Step 2, I want to solve for x. And I have a simple little equation to solve for x. First thing I'm going to do is I'm going to subtract 2. To go from here to here, I subtracted 2. Okay, I have y minus 2 is 1/3 x plus 5. And keep in mind, I want to solve for x. Don't distribute the 1/3 step. And I'm just going to do some algebra here, some very basic algebra. I'm going to outline what I do over here. I'm going to multiply by 3. So I have 3 times the quantity y minus 2 is equal to x plus 5. That's how I went from here to here. I multiplied by 3. What am I going to do now? This x plus 5 is just x plus 5. I'm going to subtract 5, and bam. So I have 3 times y minus 5 minus 5. Pardon me. 3 times quantity y minus 2 minus 5. That's equal to x. So I have indeed solved for x. Step 3 is I'm going to swap the x's and y's. Keep in mind, what am I doing? I'm solving and finding the inverse is what I'm doing. And then step 3 says swap the x. I'm going to put x in for y and y in for x. There you go. Oh, golly gee, that was an easy step. The next thing I'm going to do is I'm going to put f inverse in for y. So right here, I'm going to put f inverse in for y, and guess what? I have found the inverse. So the inverse is 3 times x minus 2 minus 5. That's the inverse. So if I have the function, I have analytically found. If I have a function, I have by these 4 steps, I have found the inverse. If I wanted to, I could verify that by the analytical definition. I could do f of f inverse, and that's what I'm going to do. I'm going to do f of f inverse, and I'm just going to let you follow along that. I'm going to put f inverse in for x. I'm going to put this guy right here in for this x, and that's exactly what I did. Did the same thing I did on the previous step. That is equal to x, and I have to go the other way. I'm going to do f inverse of f of x, so wherever I see x in f inverse, which is right there, I'm going to put this whole guy in, and that's what I did. Do a little algebra. 2 minus 2 is 0. 3 times 1/3 is 1. X plus 5 minus 5 is equal to, you've got it, x. Okay, so that's a video over Unit 5, Lesson 2, inverse functions. And what did we do here? I go back and review what I did. I'll zoom out to where I can go the entire page. Okay, so only one-to-one functions have inverses. I started out with mappings. It's one-to-one by the definition of one-to-one. Every element in the x maps to only one y. I found the inverse mapping, what I did here. I named the domain of the inverse and the range of the inverse. The range was this domain. The domain was this range. All I really did was swap the x's, and oh, look, I just swapped the x's and y's. X became the y's, the y's become the x become the y's become the x. Second thing I did was I actually found some points. I had this other particular function. Well, all I did first is I really viewed that if AB is on the graph, then BA is on the graph of the inverse. I'm going to zoom out on here on this one here, and you can pause the video. This is another example here. This is another example of finding it. On a previous lesson, I actually found the inverse of this particular function that we used in example 2 here. I found the inverse by the same steps I did before. Wrote the steps down here, so you can pause the videos. And you can see how I got this inverse. Okay, so we certainly, this is not going to be the last time we discuss this, and we'll discuss it more. You may have to reread or re-watch this video. Alrighty.